Alright, I want to take the derivative of the inverse tangent function. As with so many other inverse functions, I'm going to use the fact that I already know how to take the derivative of the tangent. The derivative of the tangent x is the secant squared x. Right? So here we go. I'm going to take the tangent of both sides. So the tangent of y equals the tangent of the angle whose tangent is x. And what is the tangent of the angle whose tangent is x? Well, of course, that's x. So I start with y as a function here. I end up with x as some function of y. Okay. Now I'm going to implicitly differentiate with respect to x. So take the derivative of the left-hand side with respect to x. Take the derivative of the right-hand side with respect to x. I like the right-hand side. That's easy. Derivative of x with respect to x is 1. Derivative of the tangent of y. Well, if I took the derivative of tangent of y with respect to y, that would be the secant squared of y. But I'm not taking it with respect to y. I'm taking it with respect to x. So the chain rule says multiply by dy dx. Solving for dy dx, I get this. I'm going to pause right here for a moment to ponder the import of this statement. The derivative of the tangent of x with respect to x is secant squared x. The derivative of the inverse tangent of x with respect to x is 1 over secant squared y, because the derivative of the inverse function is the reciprocal of the derivative of the function with the other variable plugged in. This is, however, a completely unsatisfactory answer because I didn't start implicitly. I started explicitly, so I don't want my answer in terms of y, I want my answer in terms of x. So I've got to somehow get back to x's. Well, I need a relationship between x and y. I have either the original one or the inverted one here. Either way, I see a trig function here, so there's got to be a triangle involved. So I've got a triangle. Y is an angle here, and the tangent of y is equal to x. Well, tangent is the opposite side over the adjacent side. So if I make the opposite side 1 and the adjacent, opposite side 1, adjacent, try that again, opposite side x, adjacent side 1, and make that a right angle, of course, then what I have here is a triangle that shows the same relationship between my two variables, x and y, as either one of those equations. Tangent of y is equal to x. Y is the angle whose tangent is x. Right? But because I have two sides of a right triangle now, I can get the third side by Pythagoras. So I got the two short sides. I'm going to square them and add them up. 1 squared is 1 plus x squared. Right? Take the square root. And so now I can see what the secant squared of y is. The secant squared of y is the hypotenuse over the adjacent side. Well, the secant of y is that. So I've got 1 over... The secant is the square root of 1 plus x squared over 1, and I want the secant squared. Well, that's just 1 over 1 plus x squared. What did I end up with here? Well, I started with y equals the inverse tangent of x, and I ended with that the derivative is 1 over 1 plus x squared. Again, like the inverse sine, the answer that I get here looks completely different than the function I started with. Right? I started with an inverse trig and I end up with this rational function, polynomial divided by polynomial. It just feels like I'm in a different world, but it turns out this is correct. Also, at this stage, it doesn't look so much like the derivative of the inverse function is the reciprocal of the derivative of the function with the other variable plugged in. That's when you still have that other variable plugged in. You convert that y back into x's and it ends up looking like this. Notice, though, that the derivative, that this function really does look right, because when I look at the graph of the inverse tangent, it's a sideways tangent curve, right? If I kept going, I could keep drawing that tangent curve up the y-axis. It heads all the way off to minus infinity and plus infinity in the x direction. It's got horizontal asymptote of pi over 2 on the top and of minus pi over 2 on the bottom. So if I look at the derivative, if I look at what the slope of the tangent line is doing, over here, well, actually through the whole thing I've got positive slopes. It's always heading uphill. But these are very small positive slopes, close to 0. Right here, it's as steep as it might be. And it turns out it's, I don't know, slope of 1, I think, right here. So pi over 2 would be right in here. So this does something like this, and then back down again. It's kind of a bump. Pretty simple. But if you look at the graph of this function right here, when x is equal to 0, this is at 1. That's the highest it ever gets, because when x gets bigger than 0 or less than 0, x squared becomes positive. This denominator gets to be bigger than 1. 1 over that is smaller than 1, and it heads downhill from there. Right. This is exactly the type of function you need to describe the slopes of tangent lines to the inverse tangent function. Okay. There you go.